But we're going to spend today talking about types of bonds, and we're going to get into some Lewis structure ideas, which is going to apply that idea of dots that you did for that post lecture last night. So let's kind of start with the basics here. When it comes to chemical bonding, there are three primary types of chemical bonds. There are ionic bonds, bonds that are formed by charged particles being attracted to each other based upon opposite charge, a positive charge attracting a negative charge, and the electrostatic attraction that exists between those two. There are covalent bonds. Covalent bonds are bonds that result from the collective sharing of electrons in atoms. And in particular, in both of these cases, well, and really, for that matter, all of these cases, the electrons that we are talking about are what we would call valence electrons. That is, electrons in the outermost energy level. These valence electrons are responsible for all of the bonding that takes place within an atom. And so, why did we spend the time that we did talking about electron configurations? Well, it was mainly and primarily to help us to identify what electrons are available for bonding and what electrons are not available for bonding. So if I look at an electron configuration and see, okay, krypton has a full outer energy level. Its configuration is argon 4s2 3d10 4p6. That fourth energy level, its last energy level, has 8 electrons in it. And as far as outer energy levels go, that is pretty much the maximum. And so to that end, krypton doesn't do a whole lot of bonding because, well, it has no real need to. So in ionic bonds, the formation of the ions is to get to a stable charge that leaves behind an outermost energy level that is full. In covalent bonds, electrons are collectively shared between atoms, and we do get some electrostatic attraction that occurs, not between a positive charge ion and a negative charge ion, but between the electrons of one atom and the nucleus of another. If we get them close enough to each other, the valence electrons of this atom and the nucleus of this atom are close enough to each other that they can actually interact with each other. And that's what a covalent bond essentially does. We have electron clouds overlapping, and the overlapping of those electron clouds allow the nuclei to attract the electrons of the other atom. Metallic bonds are completely different. In metallic bonds, what we have are valence electrons from the metal basically being donated to a collective pool. Most textbooks refer to this as a sea of electrons. And so what happens is if I have, let's say, a crystal sample that's got 1,000 iron atoms in it, every one of those iron atoms, if I look at the electron configuration of iron, has 2 valence electrons. So if all 1,000 of them give up their 2 electrons, there are now 2,000 electrons being shared collectively by those 1,000 atoms. And as a result, the atoms are kind of held together in this compact matrix, attracted to each other's electrons. But because of this fluidity of this sea of electrons, metals tend to have other properties that we don't see in a lot of other kinds of compounds. Bendability. The fluidity of that sea of electrons allows the substance to be a lot more flexible than other kinds of substances. Shininess. The ability of that sea of electrons to vibrate at a resonant frequency allows it to reflect light off of it because those electrons are vibrating at the same frequency and pushing back a little bit of the light that they get as excess. So a lot of those things that we talk about with metals, those properties that are special to them, conductivity, the fluidity of those electrons allows electrical current to go from one end of the matrix to the other with virtually no resistance. So between all of those, that's where we get metallic properties. And it's the sea of electrons that allows that to happen. And so if we look at the three individually, with covalent compounds, we usually see a loose network of molecules making up a sample. When they are in condensed phases like liquids or solids, covalent molecules form loose associations with each other. In the solid phase, they can sometimes form these more complex networks of atoms. But for the most part, they're just individual molecules that happen to be close to each other. And for those reasons, those individual molecules that happen to be close to each other, it doesn't require a whole lot of energy to break them apart from each other and turn them into a liquid, turn them into a gas. Ionic compounds tend to form these crystalline structures, but because the ions themselves are so large, and because the charges are so defined, the crystals tend to be larger and they tend to be more brittle because there's no fluidity in the charges in terms of their movement. And so if I execute any kind of stress on that ionic crystal, it shatters because it doesn't have a way to maneuver that stress to allow it to stay intact. Whereas with metallic compounds, we see usually a very compact structure. We get lots of atoms very close to one another. Each one of these atoms can be touching anywhere between 8 and 12 other atoms, depending upon how they're packed together. And they're all associated with each other based on that sea of electrons. And so as a result, they're very much more well associated with each other than the ions in the ionic crystal. Now, that's about as much as we're going to talk about metallic bonding. If you want a real good in-depth investigation into how they pack together, why they pack together, what kinds of properties come from that, in Gen Chem 2, Chem 106, we do a lot of that kind of discussion in our solid state unit, which is usually one of the last units that we do in the spring semester. But we're not going to really say much more about it here because it's not terribly relevant to what we're going for out of the next couple of chapters. What is relevant is ionic bonding. Ionic compounds make up the majority of the compounds that we work with in laboratory. Covalent compounds make up the other large percentage. Again, metals make up a very small percent of what we actually work with. So how do we form that ionic crystal? After all, elements are not naturally in ionic states. They're in elemental states. They're neutral. But if I'm going to make something like sodium chloride, NaCl, how do I go about doing that? Well, the answer is really simple. I take sodium metal and I expose it to chlorine gas. And if I do it at the right set of conditions, the right temperature, the right pressure, the right environment, I can get sodium chloride. But what does that look like from an energetic standpoint? Well, we have some ways of knowing. First of all, we know that when it comes to sodium, to take an electron away from sodium, its ionization energy, it's going to require 496 kilojoules of energy per mole of sodium. We also know that according to the electron affinity of chlorine, chlorine will give back 349 kilojoules per mole of energy when it grabs that electron based on its electron affinity. So just in the simple energetics of the sodium ion or the sodium atom giving its electron to the chlorine atom, our net energy is an energy deficit. It requires nearly 150 more kilojoules of energy to rip the electron out than it does to put it into the chlorine. And that's not even to mention the amount of energy that we have to put into the sodium to get it into the gas phase so that we can take the electron from it. And the amount of energy that we need to break the diatomic chlorine molecule into chlorine atoms so that we can separate the individual atoms from each other. So from an energetic standpoint, this would seem to require a good bit of energy to do. And yet salts are so prevalent. And if I look at the reaction itself in action,
sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
All right, so something's not adding up here. I just talked about all the energy that has to go into the reaction in order to make a salt. But yet when we actually make the salt, when we take sodium metal and chlorine gas, put them together in the right circumstances, the reaction isn't energy inputting, it's energy outputting. There's so much extra energy that we see a fireball inside of the reaction chamber. We see all of this heat being generated. We see the sodium chloride being formed in this almost smoke-like state that eventually condenses down into powdery solid. So what gives? Why is this energy release so negative, so much output, when everything that we've talked about thus far requires input? So take a couple of minutes, jot some ideas down, and we'll come back and talk about it and see if we can come up with an answer. All right, anybody got an idea? All right, go ahead, Ben.
Because it's an ionic bond, ionic bonds don't have a lot of energy holding together.
Okay. Not exactly what I'm going for, but we're on the right track. It does have something to do with the ionic bond. Wes? Well, the moving of the electron from the sodium to the chlorine we've already talked about. But you're both dancing around something that is important, and that is we haven't accounted for one aspect. We've done the nuts and bolts. We've gotten the sodium up to a gas. We've taken the electron away from the sodium. We split the chlorine molecule into atoms. We gave the sodium's electron to the chlorine and made a chloride ion. What we haven't accounted for yet, those two ions attract each other. And in their attraction to each other, they're going to release energy. They're going to form a bond. Formation of bonds always comes with a release of energy. How much energy? Well, it depends upon the strength of the bond. The stronger the bond is, the more energy that is going to be released. And ionic bonds happen to be pretty strong, attractive bonds. So even though we put a ton of energy in to get the reaction going, in Chem 106, we would call that activation energy, the energy that kind of kick-started. Once that energy input has been put into place, the formation of those bonds will start to release energy, and that energy initially will fuel the rest of the reaction to proceed, and then the excesses start to come off in the form of heat, light, sound, and other forms of energy transfer. For ionic bonding, there's a special name that we put to this electrostatic attraction. And it's called lattice energy. Now, the textbook definition of lattice energy focuses not on the coming together of the ions, but rather the pulling apart of the ions. So, by definition, lattice energy is how much energy does it take to pull apart 1 mole of a sodium chloride or any kind of salt crystal. In this context, since we're talking about the formation of a crystal, that energy wouldn't be an energy input, it'd be an energy output. Because again, formation of bonds releases energy, breaking of bonds requires energy. Now, we can quantify lattice energy using something called Coulomb's law. Those of you that are in engineering programs, if you're not familiar with Coulomb's law, you're going to become familiar with it when you start to take electricity and some of those kinds of dynamics courses, especially if you're thinking about being an EE. We're not going to actually calculate any lattice energy using Coulomb's law, but you do need to associate with some of the terms. The terms that we need to become familiar with are these Q terms, which indicate charge, and this R term which indicates distance. Now for the distance between ions, this is where that knowledge of those ionic trends from the periodic trends part of chapter 3 come in handy. Now the relationship here is pretty simple. Charges, the higher the charges are, the more attraction is going to exist between the two ions. So a +1 charge doesn't have nearly as much attraction as a +2. Same thing as a -1 and a -2. The greater the magnitude of the charge, the more attraction we're going to see between those two ions. Radius works in the other direction. Ions that are close to each other attract each other more. Ions that are far apart tend not to attract each other as much. Now in a crystalline structure, the ions are going to be as closely packed to each other as possible. So what is the driving force for this radius? It's the size of the ions themselves. If I'm comparing a chlorine ion versus an iodine ion, chloride ion versus iodide, the iodide we know is going to be larger. And so its larger space is going to mean less attraction to other ions. Because, again, it's the electrostatic attraction. It's the distance between its nucleus and the electrons of the other atom. And if its nucleus is surrounded by 6 energy levels of electrons of its own, it's going to be a lot more difficult for it to feel the electrons of the other ions. And so as a result, it's not as well put together. It's not nearly as attractive. So here are some common lattice energies. And these are for the whole thing. So look at the trends individually here. So take, for example, let's look at charge. Let's compare sodium chloride versus its next door neighbor, magnesium chloride. Chloride ion is exactly the same size in each case, has exactly the same charge. Primary difference between sodium chloride and magnesium chloride is the charge on the magnesium, which is double. And what do we see? Well, we see nearly a tripling of the ionization energy. Where does that extra factor come from? Well, you got to consider magnesium is also going to be a smaller ion compared to sodium. So it's got both things going for it at the same time. It's got a larger, it's got a larger charge and a smaller size. Both of those factors are going to play a role. If I compare sizes, keeping a look at my sodium chloride, I can compare it to lithium chloride and potassium chloride and cesium chloride. Chloride ions the same in each of them. Charges are the same in each of them. The only thing that has changed here is the size of the ion. Lithium is smaller than sodium. Sodium is smaller than potassium. Potassium is smaller than cesium. And notice that as my size increases, my lattice energy has decreased because those ions are getting larger and larger and becoming less attractive as a result. And this trend holds up in lots of different cases. So compare all of these oxides. These oxides are all +2, -2. +2 from the alkaline earth metal, -2 from the oxygen. Primary difference between them, magnesium is smaller than calcium, calcium is smaller than strontium. But notice that the magnitude of charge here, comparing strontium oxide to strontium chloride, we're seeing a bigger difference. Why? The oxide ion is a -2 charge, the chloride ion is a -1 charge. And it's also smaller. So that's lattice energy, the energy that holds together a crystal of a salt in an ionic compound. And it's dependent upon those two factors. Charge first and foremost, and then ionic size, the distance between those two ions. Now in covalent bonds are formed in the sharing of electrons. And we can classify a covalent bond based on two factors: bond length and bond energy. Now we'll talk more about bond length and bond energy on a later date, probably next Wednesday is when we'll talk about bond enthalpy more formally. But what we can see in this is that there is a definitive trend, and the trend very closely mirrors what we just talked about with ionization energy. Not so much with charge, but the idea of internuclear distance being affected by sizes of those atoms that are bonded together. And also, not by charge, but rather by the number of covalent bonds that are in between the two atoms. So how many electrons are being shared? Talked about this already with metallic bonds. Metallic bonds are formed through that sea of electrons, and we get a good conductivity as a result of that. And like I said before, if you're really interested in this and you have to take Gen Chem 2, Chem 106, we'll talk much greater depth about this in that course. So how does what you did last night integrate into what we just talked about with bonding? To answer that question, we're going to get into something called a Lewis structure. So what you went into yesterday in that post-lecture, pre-lecture, whatever you want to call it, was the Lewis dot system for identifying how many valence electrons were around a given atom. And there are two applications for that we can get into directly. One with ionic compounds, which you saw a little bit of in that post-lecture, and one with covalent bonds, which is going to be the primary subject of Friday's class. So coming back, going from Lewis dots again, representing here's my element, here are how many electrons are around that element that are capable of bonding, the valence electrons. A Lewis structure is an extension of this by taking those Lewis dot diagrams for individual elements and showing how those dots, how those electrons ultimately pair up to create two-dimensional structures for given compounds. Now for ionic compounds, this is usually rather simple. All that we show in a Lewis structure is how those electrons move from one point to another. So in the case of sodium chloride, we see that this valence electron in the sodium moves to the valence shell of the chloride And so sodium is now 1 electron deficient, so it has a sodium +1 charge. And the chloride has this extra electron now, so it has a 1 negative charge. And the two charges are ultimately what attract each other electrostatically, according to Coulomb's law, to make the compound.